So thanks a lot for the warm presentation and for inviting me to be here. And by the way, before I start, let me tell you to please interrupt at any time for comments or questions. It really makes it funnier for all of us. And in this talk, I will tell you about several topics I have been investigating in recent years. And although they will span different research directions, I hope I make obvious what is really the common thread that really gathers all these topics and showcases my perspectives towards beyond the standard model research. And because this is sort of a colloquium, I thought maybe not everybody is from a particle physics background, so let me tell you very quickly what the standard model itself is. It is essentially our 18 parameter puzzle with which we try to build at least our visible universe. And this is really a very, small Lagrangian that really fits a t-shirt or a cup, as many of you might have seen. And this is a theory that we have been tested a lot in very different environments with very different precision and energies. This is a summary plot of searches conducted at the Large Hadron Collider at CERN, where we basically smash protons and can produce all the standard model degrees of freedom. And what you see here is, for example, how really the remarkable agreement between the experimental results and the theory predictions here in gray. And this really tells you the remarkable story of particle physics so far, which has really led some people to say this is perhaps the best tested theory in the history of science, which is really outstanding. Nevertheless, we are really sure this cannot be the ultimate theory of nature. And that's because there are a lot of things actually that the standard model cannot explain. Strikingly, we don't know what the dark component of the universe is. We don't know how to add dark matter to our theory. We don't know a mechanism to generate neutrino masses that we have observed, or how to explain, for example, the generation between the sort of asymmetry between matter and antimatter that must exist at some point of our cosmological history. And the theory itself also has a lot of puzzles. For example, in the flavor sector, the fact that the couplings really span a large hierarchy in their size, large hierarchies in their size. In the Higgs sector, there are a lot of naturalness problems that I will mention in particular. And up to these, we know that the theory cannot be consistent up to very large energies, because eventually, for example, we will meet effects from gravity at Planck scales. So we know we really have to work hard to go and advance our knowledge about nature. The real question is, where do we start, right? Where do we start to actually build a more complete theory? And in order to do this, we tend to think about the parameter space of new physics, which can be a new particle with a different coupling and mass than the ones we see in the standard model. The point is that actually today we don't have any no-lose theorem, so we really don't know where and when we will make the next discovery. But this, however, does not mean we need to search blindly, because many of these puzzles I told you about actually hint towards some particular energy scale. For example, Higgs physics and the hierarchy problem that I will mention just in the next slide are still important motivations to expect that something should happen near the Higgs scale, near the tera-electron volt. And in the second part of the talk, I will also focus on motivations in a more feeble parameter space in this region over there that can motivate new physics in the form of particles which are light and more weakly interacting. So indeed, let me start with motivations for high energy new physics. So I think everybody is more or less familiar with the hierarchy problem, which concerns the Higgs boson that we have observed already, so we know its mass. However, an elementary scalar particle like the Higgs, as we know it, its mass is actually not protected by large UV corrections, which means that if we imagine that there are new scales, new heavy scales that we need at some point to include in the theory, which can come from the scales associated, for example, to grand unified theories, resonances that also appear in seesaw models for neutrino masses, etc., or the Planck scale itself. At some point, they should be able to communicate with the Higgs. And this poses a problem, which is really just dimensional analysis. You have a high scale, the Higgs is not protected, so the mass should naturally be of the size of that heavy scale. And now we know this is not what happens, because we have measured a light Higgs. So what does this mean? I will definitely not overview these popular solutions, but at the time, even before the Higgs was discovered, people were certain that something should be there close to the Higgs scale to protect the Higgs mass, which typically involves new heavy resonances like superpartners or composite resonances or Kaluza-Klein modes in models of extra dimensions. And all these partners, to sort of shield the Higgs mass from corrections, should appear at a scale not so far from the tera-electron volt. And here is the status of our searches. My goal is not to go in detail into them, but essentially the many searches we conducted at colliders already push all these resonances above a few TeV. And this, of course, puts a lot of tension in the naturalness arguments and in the motivations of these theories to solve the Higgs hierarchy problem. So the question now is really, what's going on? And I definitely think that this is not a problem that we should simply neglect, because it is something really deep. It's about, it uses a principle that we have used throughout our history in particle physics, which is the fact that, UV scales should not care about what happens in the IR. This decoupling of scales is really what allows us to make science. And so this is really a deep problem to explore. Something should be there to protect the Higgs mass. And this something should take the form of new physics. And this new physics can indeed be new particles, as these models are guiding us into. So now the question, if we think about the hierarchy problem as motivation to new particles, is where are they? And so if we still want to use motivated models for these problems, we need to explain why they have not appeared in our experimental searches. So the question is really, are we looking at these models in the correct region of parameter space? How do we break the signal of these models in these regions and motivate others? And I wanted to talk a bit about this perspective. But another is that, you can imagine that we explore this high energy frontier and we find nothing. So what does this mean? And this is a more radical point of view, but still is something interesting, because new physics does not always come in the form of new particles. So if indeed we go on and find nothing, maybe the Higgs is telling us about new principles in nature, who knows, which will really make us question our foundations and build a more fundamental language beyond quantum field theory, who knows. And you might think this is not very interesting, but I would argue that as long as you can define what this unconventional new physics is and search for it experimentally, the paradigm can still be interesting. So I will briefly mention also some recent work on this direction. Okay, but let me quickly tell you about the conventional things and how can these things still be motivated and appear in new regions of parameter space. Here I picked the idea of composite Higgs theories. So let me just briefly tell you what this is about. These theories, to protect the Higgs mass, they basically explore a trick that we know nature has already, which is the capability of generating confining sectors. So essentially what these models propose is a new strong sector, but now at scale, like QCD, but now at scales of the tera-electron volt. And so at this new confining scale, you would expect all sorts of resonances, like new vectors, new vector-like fermions, that all play the role, for example, of the rho meson in analogy with QCD. And the Higgs here is assumed to be produced as a goldstone from a new global symmetry of this strong sector that should be spontaneously broken. So in this case, the Higgs is protected by two things. The fact that above the confining scale there's no Higgs, and the fact that it's a goldstone of a new symmetry, so it's naturally lighter than the other composite resonances. And searches for these models have relied on this minimal paradigm. So basically, searches of compositeness have assumed that we might have these extra composite resonances at the TV scale, and they can only decay into the standard model. But a realistic model of these composite theories might actually produce extra goldstones in conjunction with the Higgs. Because, forbidden this case is like assuming that because of minimality, QCD would only produce one pion, which is not true. So if you have this extra scalar sector, which really corresponds to a set of pseudo-Goldstone particles, actually, you can naturally have much more regions for naturalness for these composite models. And to me, it's really impressive why they are not being searched. And I did a lot of work trying to also motivate these searches, but something else I wanted to talk today would be also on the relevance of this extra scalar sector to address some shortcomings of the standard model and also populate new regions of signal for these models. So to do that, let me just concretely mention some smoking gun signals of these theories. So of course, at some point we need to deal with the fact that these heavy vectors or heavy quarks, like top partners, they need to communicate with the standard model fermions. This depends on the flavor structure of these theories, and the current paradigm that people use is that of partial compositeness. I'm happy to tell you more about this if you're interested, but I wanted to focus on something else, which are really universal signatures. And this is, for example, the coupling of the vectors, the heavy vectors that we have in the theory with the Goldstone particles themselves, here in the second diagram, that because they are part of the same strong sector involves a strong coupling, G star. And moreover, we also have interactions among the Goldstone particles themselves. And interestingly, the leading order interactions for this scalar sector, they need to preserve the Goldstone symmetry, so they are of the derivative form. And this is very interesting for phenomenology, because you can imagine that one of these Goldstone particles, here denoted eta, can be dark matter if it's stable. And you see here that the portal coupling that it has to the Higgs is not, actually depends on energy. So it's not what we typically think about for WIMPs. And this is really nice because these interactions being enhanced with energy, with momentum, they can be really large at the annihilation scale and per se actually generate all the relic abundance we observed. But at low scale experiments like direct detection, they are naturally suppressed. So this is a model, some people say WIMPs are dead and so on, at least the simplest WIMP, that a singlet, scalar singlet that talks with the Higgs, and this is simply not true. Here's a WIMP that evades all of these and is protected from the hierarchy problem. So I work a lot on this in this paper, taking also into consideration other Goldstones that can offer new annihilation channels for dark matter. But to tell you some other application in more detail, I chose here to talk about signatures, about this strong coupling between the heavy vector, composite vector, and Goldstone particles that here I'm denoting A1 and A2. So I told you before, this heavy vector being composite is likely to appear at scales of around the TeV, where our new compositeness scale lies. So we can sort of integrate it out and see that this kind of coupling can give rise to B decays into these pseudo-Goldstone particles. And essentially, they come in association with the Higgs, so they sort of couple like the Higgs. Their couplings are Yukawa suppressed, so in the low mass region, they can give rise to a fermion final state. This has been searched at experiments, and it already sets constraints on this coupling. But what we can realize quite easily, having a full model in mind, or just imagining more than one coupling at a time, is that if now we have a non-minimal scalar sector, obviously, these particles can interact among themselves. And the heaviest one, here denoted A2, can decay into the lightest. And in this case, if this branching ratio is larger than the branching ratio into fermions, which typically is, here is a very easy way to explain why your model would evade the 4-muon search. And in this case, this decay would instead give rise into 6 muons, which is a final state that was never looked for before at experiment. And you can even deform more the UV and think of, and see what are the implications. For example, if these two scalars are close in mass, your model enjoys a larger symmetry, and it turns out that the B decay I just showed you, the two-body decay, is closed, and the only way to probe the model would be via an extra particle. And I chose this example to tell you about, because I wanted to note two things. First of all, these are not really, very hard things to find in model building. These type of models can totally exist. I can totally produce two Goldstone particles which are close in mass or not. So these are important regions of signal of motivated models that we need to search for. But there's something else. In this case, you see that my final state from a B meson would contain a lot of particles. So these particles need to share the energy among themselves. So they will be very soft at colliders. They will have a very small energy or momentum. And it turns out our detectors, up to like a couple of years ago, were not even recording these events because of trigger requirements. So these detectors were mostly focused on heavy new physics, so these kind of scenarios would completely evade the searches. So these kind of studies are also important to motivate the experiments and make us look beyond what they looked for already. And for example, in this paper I studied with collaborators from the LHCb experiment, really, which kind of analysis could we design to see this kind of process. And we also study scenarios in which these scalars can be long-lived. And if you have a particle that is long-lived, it might not decay in the main detector of an experiment like the standard model particles. It can decay further ahead. So here we were exploring different types of tracks and how they could help us in actually probing this strong coupling between these A1, A2 particles and the heavy vector. And this is really important, the use of these different tracks across lifetimes. In the end, this actually motivated the experimentalists to do this search. So they are currently applying it to data, and we will hear the results soon. Okay, and at this point, I will move on to a different thing. So if there are questions, I will take them now. Otherwise, I wanted to tell you about something else, because I've been talking, I gave you examples of how we can use conventional UV models, in this case composite Higgs, and still probe and motivate unconventional parameter space. But this is based on the fact that you have chosen a model, a complete model to probe. What if that model is really not the true model of nature? And the cool thing about the next thing I'm going to tell you is that we can probe new physics even if we do not know how they look like at high energy. And this is using the tools of effective field theory. So basically, here we have the standard model with the couplings we know, and we can simply just gather operators which are non-renormalizable, and all which are compatible with the degrees of freedom we know and the symmetries that we also know of our theory. And the point here is that this expansion, being completely generic, it can track down any effect of new physics that you would put in the ultraviolet. Essentially, if you want to have a UV picture in mind, you can imagine a heavy mediator, and you're integrating it out. So you're doing an expansion in which you assume that the energy you have access to is actually smaller than the mass of these heavy particles. So you're looking into, for example, an observable and seeing what happens next to a tail of a new resonance, because you cannot solve it completely due to your lack of energy. And this is very interesting because we can search agnostically for these new physics. And in order to do so, however, you really need a power counting. You need to assume something regarding the size of these Wilson coefficients, okay? So typically people do a naive power counting, which is to say, I have no way, I don't want to assume that the UV has any preference in these Wilson coefficients. So in this naive power counting, you just study what is less suppressed by the cutoff scale, which is, it roughly represents the mass of the new resonance you cannot produce. So in this case, dimension 6 would be the leading interactions up to lepton number violating operators. But you know, other power countings are interesting, and I will tell you about some of those. Before, let me just tell you what would be really the goal of this effective field theory program. So the goal is, of course, eventually you find an anomaly. You find an evidence of a non-zero value of one of these Wilson coefficients, and you say, even if you don't have that, right, which is where we live now, we can still constrain this parameter space of Wilson coefficients with your experimental bounds as they get more and more precise, and that is indirectly constraining what could be the UV theory of nature. And something fun about this is that you might think that different UVs can populate different parts of this parameter space. They might be simpler or more complicated, but a priori, why not? And this is actually not true, because if your UV is really standard and it respects the core principles of quantum field theory, like unitarity and analyticity, there's a dispersion relation that your Wilson coefficients need to fulfill. And here they are only restricted if they grow enough with energy. So actually, these constraints, which are called positivity constraints, also affect operators starting at mass dimension 8. And essentially, what this means is that their sign is constrained to be positive. And this is really cool, in my opinion, because it means that if you actually ever make a detection of a Wilson coefficient in this region that violates this bound, which I will call the Swapland region, this means you make a double discovery, because you're seeing something beyond the standard model and something that is truly exotic. And even though this is really, really, truly exotic, we cannot imagine what this is. I think as an experimental program, it's very interesting to wonder, would we ever be able to detect such a thing? And can we actually motivate new physics that will not appear at dimension 6 and only at dimension 8 to sort of make this Swapland test? And even more interesting, I think, is whether we can associate this test to the hierarchy problem and unconventional solutions of it. So all of this, again, is connected to the idea of power counting beyond naive arguments. And this is, by the way, a work that I'm doing with Jaime and Javi Serra, which is about to appear. The standard way to protect the Higgs mass, assuming it is a Goldstone particle, is via this kind of shift symmetry, which is non-abelian. This is what protects the Higgs in standard composite theories. And this kind of shift symmetry that protects the Higgs mass in a 2-to-2 scattering appears as a contribution that grows with 2 powers of energy, okay? But, you know, purely from the IR perspective, and that's what we want to do if we really want to probe unconventional UVs, if we don't want to think about the model as your first attack to the problem, but instead purely go from an IR kind of perspective, it's very easy to conceive other types of new symmetries for the Higgs. What if the Higgs actually obeys an abelian shift symmetry? If you know, the symmetry breaking pattern that produces this Goldstone is actually more restricted. In that case, the leading order interactions would not start at dimension 6, but start at dimension 8, okay, and grow with 4 powers of energy in a 2-to-2 scattering. This is the case that we call abelian Goldstone Higgs. And just for the fun of it, why not an even weirder type of symmetry, like a Galilean type of symmetry, which would enable us to start our probes of the shift symmetry of the Higgs at actually mass dimension 10 with 6 powers of energy in a 2-to scattering, okay? So these are just unconventional hypotheses, but what I was imagining was a collider analysis that could allow us to distinguish these scenarios. So for that, I need to tell you a bit about future colliders, just in a few words, and which colliders are more important to test these operators, namely in processes like vector boson fusion. And here would be the insertion of the different operators, the different scenarios I told you about. So the discussion about future colliders is a discussion about precision versus energy, as you might have heard about already. So we have linear colliders, which can gather, can explore high energies very easily. Okay, namely, there's a proposal of clique and E plus E minus collider that is expected to be able to, reach energies up to around 3 TeV. And in contrast, there's the case of future colliders, like the Future Circular Collider, which is the flagship program that most likely will be supported by CERN. And this is a precision machine. So because it's circular, it loses power with synchrotron radiation, but it can really gather a lot of statistics. And that is truly impressive. For example, in the Z-pole run, the first run of this collider, you can expect to produce all the lab data in less than 1 minute, which is really exciting when we think about constraints of new physics models. And you have more runs in which you will get to know the standard model parameters really in a really precise way, like we have the W pair run, in which we will be able to really know the mass of the W boson up to unprecedented precision. And I'm telling you about these because I'm going to tell you for these specific scenarios when one or the other is important, okay? So I told you that what really differentiates these different scenarios is energy growth. So of course, if we want to explore energy growth, we need to go to a linear collider. Here is, for example, the bounds that we would get from clique in the standard scenario, dimension 6 versus dimension 8, the abelian case, okay? And just for completeness, I also show how this bound could get better with a hypothetical muon collider that collides muon pairs at 10 TeV. What I really wanted to comment here, and I wanted you to take a look at this bar here, which shows the current bound on this standard scenario by the LHC. And you see that this bound is already sort of comparable for this operator, for this Wilson coefficient, with the bound one would get at the future collider like clique. Why is that? This is because this particular operator, the standard scenario, which corresponds to an operator that involves 2 derivatives of the Higgs, this operator contributes to electroweak precision data. It contributes to all the Higgs couplings, so we can already probe it. And at the Future Circular Collider, because essentially this scenario contributes to custodial violation at one loop, it contributes to the W mass. And I told you, we will know this mass up to unprecedented precision. And it turns out with the future collider, the current bound will be really smashed to a point. This scenario will be totally probed if we do not see anything. Nevertheless, something like the abelian scenario, which is dimension 8, it does not contribute to anything. So in this case, to probe this scenario, we really need energy. So with this, we quite easily see the complementarity between future colliders to probe unconventional, in this case, unconventional scenarios for the hierarchy problem. And to end this part, I will just show you a final test that I did, because, these operators, some of these scenarios, namely the higher dimensional ones, the abelian and the Galilean, they correspond to operators that grow enough with energy to be constrained by the positivity bounds, okay? So in this gray region in the parameter space, you have the swapland. You cannot complete an observation here with the standard UV theory. Here in the white region, you can. So I was wondering here, you know, can we actually prove that in case of discovery, we would be able to distinguish between these two regions? And so I did this exercise, which is, you know, up to now, these were exclusion bounds, assuming you only see the standard model. So of course, you cannot distinguish between the swapland. You cannot distinguish the sign of these operators because you cannot exclude the standard model. These regions, by definition, are defined around 0. But in case of discovery, this is of course doesn't need to be the case. With this discovery, we can exclude the standard model. So here I'm assuming an observation compatible with one of these abelian scenarios with a moderate strong coupling that I represent here with a star. And then I ask, given this observation, how large is the space of theories which are compatible with it at 95% confidence level? This is the region that I get. So you see totally, by having a discovery, you would be able indeed to differentiate between the two and really claim an exotic signal. So, and actually something important here is that for this test, because this test aims to probe the sign of this Wilson coefficient, you really need a clean environment at low energy beams, because low energy beams, those are the ones that can probe interference effects, while higher energy beams, of course, give you the best exclusion bound. And to conclude this part, I just find it interesting that, you know, the hierarchy problem, beyond being just a theoretical puzzle, can be really a concrete experimental program for future colliders, even if the UV is quite non-standard. Okay, and now I will make another break here to tell you about some different direction of my recent research. And now I'm going to focus on, so for now I told you about the hierarchy problem. I also talk a bit about WIMPs, so motivations for new physics around the TV. Now I'll move here to much smaller energy scales. And here I will be guided by another puzzle of the standard model, the strong CP puzzle. So what is that, first of all, in case you're not familiar with it? So this is really the question of why we have an operator in the theory that can certainly be there. It is compatible with all the symmetries we know, but it turns out to have no effect in nature. And that is this theta angle, this interaction among gluons, which is CP odd and could therefore generate a neutron electric dipole moment that we do not observe. So the bound on theta now is smaller than 10 to minus 10. And you know, you might care about this problem or not. I think that the severity of this problem is particularly pronounced given the elegance of this solution, which you might buy it as argument or not. But this is because this problem can be solved in this very easy way, which is you take this theta, which is a constant, and you promote it to a dynamical field. Then, you know, after QCD confines, you will get the potential for this theta, which now is really a dynamical field, and you can compute that potential, and you can show that this theta will stabilize dynamically in a minimum that is CP conserving. And that's how you solve the problem, okay? And you know, this dynamical field we call the QCD axion, and the QCD axion is thought to be a Goldstone particle of a new U1 symmetry that is assumed to be, in this case, spontaneously broken and also anomalous in order to have this coupling here. And for this mechanism to work is really important, of course, that this is really a true Goldstone up to this effect, because we know we want this potential that comes entirely from QCD is the one that really works to solve the strong CP problem and guarantee that the minimum where the axion is stabilized is one that is CP conserving. Interestingly, this solution is also very predictive because, you know, you can really compute the potential. This is an exercise that I think all of you could do. It just uses the tools of chiral perturbation theory, so it's just building invariants and computing the potential. And this potential shows that there's a precise, I think I'm in front of you, no? Okay, sorry. Yeah, so from this potential, you can obtain a very precise mass-scale relation for the axion that reads as follows. You find that the mass of the axion here times the decay constant, which is also the scale at which the symmetry that produces the axion is broken spontaneously. This is given by the topological susceptibility of QCD, which is essentially the mass of the pion times its decay constant squared. So this is really very predictive, and it really dictates the axion phenomenology. Beyond that, what you can note is that this relation also tells you that even if the axion is produced by a theory which only appears at very, very high energies, like a grand unified theory, you can still hope to see it, because that will only make it lighter so that you can have access to it experimentally, which is very interesting. Okay, but something about the phenomenology of the axion. This plot gathers many searches regarding the axion coupling to photons versus the mass. So the coupling here that solves the strong CP problem is really the coupling to gluons. So when we search for something like coupling to photons, you need to include some other uncertainties, because this coupling also depends on the UV content of the axion theory. But you know, for standard cases, you need to include the uncertainty, but you still have a very predictive QCD axion band, which is a target for all these experiments. So essentially, you have an upper bound on this QCD axion band from searches of axions in stars. And then you have these interesting experiments, haloscopes, that can really reach already important parts of the band. And they are so sensitive because they explore quantum resonant effects. So essentially, they are cavity searches, and they tune their cavity modes to match the frequency of the axion wave. And that's how they get so good sensitivity. And you see here the projection for the future is really that they will cover, they will cover all of it. So, you know, there's the real case that if this is really correct, if the axion exists, you might discover it very soon. Which is exciting, particularly because in this band, the axion can also be dark matter and explain the totality of Rayleigh abundance we have observed. And that just relies on this misalignment mechanism that here I will just review very quickly. So to get this dark matter abundance of the axion, we just need to solve its equation of motion in an expanding universe. Here, theta just denotes the dimensionless axion field. And here, this mass of the axion, I have to tell you that it does depend on temperature, which is a result we can get from the lattice by solving QCD. And this is important because this is essentially negligible at high temperature. So the axion is originally stuck. And eventually, when the Hubble becomes comparable to the mass, it starts its oscillations. And regarding that, it is around that time that also the comoving number density becomes constant, and you can realize that the axion redshifts as cold dark matter, and you can compute out of this number density the energy density, and find that we can, for order 1 initial misalignments, we can explain all the abundance we observed for a mass at the order of the microelectron volt. So, you know, this is really exciting. We have a predictive candidate that can solve 2 problems at once. And of course, we are led to think, isn't this too good to be true? And you know, I've been thinking about that in the last years. And a big assumption that is hidden in this picture is that the axion would be produced alone in nature. And in fact, in many UV completions from where we can produce the axion, like grand unified theories, and even models which, you know, they do a flavor deconstruction, so they put new confining groups, they include new confining groups into the theory. In those kind of setups, you typically have more than one axion. This is also sort of the generic prediction from string theory, but I will not talk about this unless you ask me. And you know, in these limits, whatever number of flavors of axions you have in your theory, they can mix. So the question is really, what is the impact of this mixing to the picture I just described, right? And in particular, I've focused on two different types of consequences of this mixing. So an obvious question to ask at 0 temperature is, are our targets, our regions of signal for axion experiments still the same? Is the QCD canonical band stable? And another question is, can there be consequences of mixing at finite temperature, namely in the way we compute the dark matter abundance that is contained in the axion field? And you know, let me tell you a bit about these. So regarding the stability of the axion band, that here I'm really plotting in the parameter space of gluonic coupling versus mass, we found out that if you have a system of axions that can mix and you still want to solve the strong CP problem, actually there is a sum rule that your system needs to obey. And this sum rule is interesting because it is written in terms of observable quantities. So it is written in terms of these G factors, okay, which essentially measure the distance of a given signal to the QCD canonical band. And the requirement is that in an n-axion system, the inverse of the G factors needs to sum to exactly 1 to solve the strong CP problem. So the first straightforward consequence of this is that given a signal, now we know, even if it's outside of the canonical band, now we know it can still represent perfectly a QCD axion as long as it's not the only signal we observe. And many patterns of axions are now possible as long as they, they fulfill this sum rule. So in this regard, we also ask, what is then the most exotic configuration we can build, the most exotic pattern we can build far from the canonical line that maybe allow us to motivate radically new regions of signal for axions, for axion experiments. And we found out that this needs to involve a large number of fields. And these large number of fields they can lie really far from the QCD axion line if they appear in these sort of patterns in which they are aligned in the same line parallel to the QCD canonical line and a factor of square root of n away from it, where n is the number of axions in nature. And why are these the most exotic configurations? Because, to preserve the sum rule, if you try to push one of these signals away, the other has to compensate by going closer to the line. So that's essentially the intuition. So, I was for a time really obsessed with this, and I wanted to know which kind of UV models could give you this kind of IR pattern. And that's the way I think effective field theory results, like the sum rule, should be used. You use an effective result to find something different that we have not yet thought about, and then you try to build a UV model to deliver this kind of result. And it turns out, I told you I need a large number of fields for these, so a natural setup to think about in this context are models with extra dimensions. And here I will be really very brief. And the way we get this large number of fields is because if you include an extra dimension where gravity propagates, but you also allow a fifth dimensional axion to propagate in the bulk of this extra dimension, what you realize, and this is a very well-known result, is that when you integrate that dimension out, when you compactify it to obtain your 4D effective field theory, 1/5 the axion becomes a tower of 4D scalar modes known as the Colloquia modes. So we naturally have these large number of fields in these setups, and moreover, this model is very predictive. The structure of mixing in this model is very predictive, and I will not go through the details, but essentially what we found is that in these models we can naturally have these patterns I was telling you about, where all the axions are aligned in a new QCD axion line, which can arbitrarily go far from this canonical line in the limit where, you know, in the flat case, in the limit where the size of the extra dimension is larger, comparable or larger than the QCD axion mass, the standard QCD axion mass. So, of course, going to the limit of large extra dimensions is problematic because they are bounded by fifth force searches that search for KK gravitons. But you know, this was a very cool exercise for us to know when these patterns are possible and to think about different types of constructions with extra dimensional models, which would be less constrained phenomenologically. But okay, to the last part that I wanted to discuss regarding axions is the fact that even if you don't have this mixing, okay, if you have two flavors and you know the external mass that you're adding on top of the QCD axion mass is decoupled, so we don't have any of these phenomena, even in that case, you need to worry about cosmology. And you know, here I'm just generalizing what I told you about solving the axion equation of motion in an expanding universe for a two-axion system. And here I'm showing you the evolution of the mixing angle in time. Why does the mixing angle evolves in time? Because the QCD axion mass evolves in time. Okay, so this is not an extra ingredient that I'm adding to the model. This is already there. And you know, even if at zero temperature, at late times, this mixing is negligible, because of this time dependence, it could be that you go through a point in the cosmological history where this mixing is maximal. And in terms of mass evolution, this just represents the point where the mass of the QCD axion, here represented in the dotted line, crosses the mass that I'm adding for the other flavor, that here I will call the sterile axion. Okay? So this point of maximal mixing is when these two masses cross. What this represents for the physical states of the theory is that, you know, before crossing, for example, your light state is identified with one flavor, but after crossing at late times, it changes drastically its composition and becomes identified with a sterile field. So now if you remember the misalignment mechanism I discussed before, what are the consequences of these? Well, let us assume we are in a scenario where the initial field amplitude of the light field is the largest, okay? Which actually occurs quite generically. So let us follow the light field. So at early times, the light field is just like the QCD axion. So eventually, when we compute the number density at oscillation temperature, we will get the same number density as we get in the single axion mechanism. But what happens at late times when I need to extract the energy density? So essentially, as I told you, after crossing instead, the composition changes. And when we compute the energy density, which is this number density times the mass, we don't get the axion mass. Instead, we get the mass of the sterile field. So this shows you quite easily how your prediction can change. For the standard mechanism with one flavor, this would be Na times Ma. Now you get a suppression by the mass of the sterile field. And you know, this is actually dramatic for axion searches, because what this shows is quite easily the sterile field here can be the dominant dark matter component. And because the sterile flavor has no business in solving the strong CP problem, it has no business in staying close to this yellow line. Okay? So it can be found really down into this deep purple region. And you might say, okay, fine, then this just means that all these searches which are targeting the line will not see dark matter, but they will still see the QCD axion. This is not true because actually all these haloscope searches assume that a given signal is 100% of the dark matter. If this is not true, you can drastically reduce the flux that these experiments get, the flux of particles. And so if the axion is really not the dominant dark matter component, the projections get much weaker, and you might not be able to actually discover an axion in the next few years. So I think this is really important and means that the strategy for haloscope experiments, in my point of view, should really be reanalyzed, and maybe it's worth for these experiments to, instead of trying to just quickly cover all of these bands, they spend some time going beyond it to try to give better limits to still probe these kind of scenarios. Right, and I think at this point I am mostly concluding. I have, I think, 3 minutes more to tell you about really recent research about something else. And here I will just pose the question I'm thinking about in these last months, no results. And this concerns a more generic question about dark matter. Because, I told you about different types of candidates, at least 2, WIMPs and axions. But, the landscape for dark matter is really huge. Essentially, things work. You have many constructions that work from 10 to minus 20 eV to the ballpark of solar masses. Which means that dark matter is perhaps the most challenging problem we have, and also we really need hints from data. And it seems, luckily, we might have some hints from astrophysical observations. Basically, the way this works is to know about dark matter at galactic scales or even larger scales. One thing that you try to do is you simulate the universe in a computer, and then you see which structures you get. Then you look at your data from astrophysics, telescopes, and so on, and you compare what you get with what you observe. And in many galaxies we observe, it turns out that we see, when we look into the dark matter, when we reconstruct the dark matter density profile, we see that in the inner part of the halo, most of the galaxies, or at least a large fraction of them, they produce cores instead of a cuspy profile, which is what you would get by simulating cold dark matter without collisions. So this really raises, and this discussion started years ago, the question of whether this means that dark matter has self-interactions, okay? And this would be really exciting because we would learn more about dark sectors and really be able to reduce more parameter space of these dark matter models I just showed you. And the situation is really not yet clear because the galaxies we observed so far have a lot of baryons, so baryon feedback is important. But soon we will get cleaner environments and better conclusions from analyzing dwarf galaxies. So it's still important to understand how to implement these self-interactions. I just have 2 more slides on this. And why is this an interesting story, I think? It's because in these cosmological simulations in the computer, you don't scatter particle dark matter. You don't scatter WIMPs, for example. What you do is you scatter these big clusters with solar masses, which are really representatives of these are completely numerical particles, not real particles. You need to do these because of simulating dark matter is just not possible with the computers that we know of. And these numerical particles that we use in cosmological simulations, they are identified with coarse-grained phase spaces. What does this mean? So the basis for these simulations The basis is the Boltzmann equation that I think everybody knows. So the Boltzmann equation tells us how the phase space of particles at a given position with a given velocity, how it changes due to self-interactions, due to scattering. Here's the particle physics, okay, in this cross-section. And now what is assumed for the scattering of these numerical particles is that you can sort of average out this Boltzmann equation and use a coarse-grained version of this phase space, which is this f hat, and you simply assume that this phase space evolves with the same equation as your particle phase space. And we were really puzzled by the fact that there's no really first principle description of this coarse graining, and namely you just assume, that the cross section that appears here is not affected by this procedure. So you assume that particles interact with the same cross section as these big macro objects. So we were really puzzled about this question. This is what I've been working on in these last months, going a bit insane with it, but I have Mary Angela, she's an expert on these cosmological simulations from Princeton, and we also are discussing with Tim Cohen, and we are getting this a proposal. We are obtaining one of these mappings, and we want to propose it to the community. And I just wanted to finish this by saying, answering this question, I think it's really important because it means that, if this mapping is not trivial, and it has no reason to be, all your interpretations, model interpretations of the results of this simulation and the things that you're using to constrain a particle cross-section and these dark sectors, they might completely not hold. So I'm really excited by this, and I hope I can share results soon. Okay, and this really brings me to my conclusions. I try to give you my perspectives, fresh perspectives towards the research in BSM, given that we are in a moment where we have sort of excluded and pushed further our best motivated models. Now is really an important time to think and build more realistic, less simplistic theoretical models. And I try to give an example as the case of non-minimal composite theories, which still serve their initial purpose and can really guide us into new parameter space, showing that new data is really necessary in some of these cases. Beyond using data to build models and using models to require new data, it's really important sometimes to also revisit the mapping between data and the models itself, because sometimes it holds assumptions that your model might not realize, as in the case of axion dark matter searches, or in other cases, I think the mapping is really not well defined at all, and we can try to put some effort to build a better one, hopefully. And to really end, I just wanted to add a perspective from Steven Weinberg himself, which has really guided me as a student, and assuming there are students around, I just wanted to share it. And this is also a justification for why I chose to present you works in really different research directions. Because I think that's the paradigm we live in particle physics. Like I said, we really don't know when and where the next discovery will be. We are really questioning our foundations, our best BSM models. But this doesn't make the field less interesting, of course. It's quite the opposite, because it really leaves room to do exciting physics and deliver creative work. So, thank you.